Okay, so we were doing area problems. And if you recall in this first example, so we looked at the portion of this parabola, which is right here, and then we're trying to estimate the area under that parabola in relationship to x equals 1 and y equals 0. Okay. And so we created these three rectangles. We found their area of each and added them all together. And so we got an approximation, but we can look at that and go, well, that's too small. So we did set up this before we left. So now we're going to do four rectangles. And of course, these are going to be above, right? Now, we can determine that the width, so from here to here is 0.25, from here to here is 0.25, from here to here is 0.25, and here to here is 0.25. So when we're finding the area of the rectangle, we've got this, then we need its height. Well, we won't do the height over here because that would be no way to find that y coordinate in that ordered pair because it's not on the graph. So we always have to choose the height for the point that is on the graph. And again, this is y or f at x equals, just to remind you, this is this parabola. Okay. All right, so we're going to look at again, if you recall, we did a t-table. So each of these would give us the ordered pair of how to get to these points. So x, if we want this ordered pair right here, we would go to the right 0.25. And then to find its height, we have to plug it into the parabola. So that would be 0.25 squared, which we actually did above. We calculated that one, 0.0625. All right, then we want to look at this rectangle. And again, on the t-table, from the origin, we would go over 0.5. That's your x coordinate. And then we would square it because that's the given equation. And we actually calculated that on our prior t-table, and that's 0.25. And that's the ordered pair for this point right here. Then we want to find the ordered pair for this point here. So it goes over 0.75. And then we're going to use the given equation. We're going to square that. And again, we did that last week, and that's 0.5625. All right, so here's the new one. So I want to know the ordered pair for this. So it goes over 1. And then to find its output, we find f at 1. So that would be 1 squared, which is 1. So that's the only new one. Okay? All right, so those are all of the ordered pairs. Now what we're going to do is we want to calculate the area of each rectangle. So if I look at the pink one, I want length times width or width times height. Now be careful for this one, yes. From here to here is 0.25. And then its height is the output here. So how tall that is 0.0625. So that's my pink rectangle. So now we're going to go to the blue. Now this is where you need to be careful. The width of this rectangle is not 0.5, right? That's just the ordered pair. The width is from 0.25 to 0.5. Its width is also 0.25. And its height, again, is this output. And that's 0.25. And then we have our orange. So now we're looking at the orange rectangle. From here to here is 0.25 again. And then its height is the output 0.5625. And then lastly, it is the width of 0.25 again. And its height is your output, which is 1. Right? Yeah. That's how tall it is. From here to here is 1. It's always the output. All right. So we're just going to put all of that into our calculator to find the approximation. So I'm going to do it quickly. You do it quickly, and let's make sure we get the same thing. Because when you do it quickly, it's easy to hit a wrong button. All right, here's what I got. 0.46875. Okay. Now, that's units. We don't know what we're talking about, and that is squared, because area is always units squared. Okay. Now, up here, our approximation, when the rectangles were below our function, we knew that to be a bit too small. What do we know about this one? It's a bit too big, right?
What are we saying it's like too big for them?
Because your area is including all of these, which is more than what's under there. Here is what we're trying to approximate. We're also in this answer including all of that. That area is too large. All right, so based upon this one that's a bit too small and this one that is a bit too big, then a good approximation is an educated guess by averaging the two. So I'm going to take that one that's too small, 0.21875, and add it to the one that's too big, 0.46875. I'm averaging two numbers, so I'll divide by 2, and that would give me a pretty good guesstimation. .34375 units squared. And that'd be a good, again, we're not guaranteeing it's exact. We're just saying that's a really good approximation. All right, some terminology we will use a lot of, and we will be learning how to find the limit. So that is probably, that's a calculus term. All right, the value that the function, you're going to hear a lot with limit, is what is that value approaching? So the value that the function approaches as the input, that's your variable, approaches a certain value of x. We'll get into that in 2.2.
So in this case, for us,
it doesn't have a limit. It's just, I'm adding some more terminology. Yeah. Okay, now before we, okay, so I've completed 2.1. That's why it's due tomorrow. Now, before we get to 2.2, this is one of the problems in your 2.1, and I've seen students that kind of were uncertain about it, so I want to kind of hit on some things on this so you can have an understanding of like the problem we just did. It won't be exactly like this, but what it relates to. Sorry, I'm looking at my phone so I can. Sorry, Ruth, I was just seeing your text.
Okay.
I need a time because I won't be back in my office till after 12:30. So I just need to know if it needs to be done before that. Okay, so I'm going to go to Desmos because I just want a visual of this is,
It should be fine after.
here's what we're looking at.
I don't have class till like 5.
We can hopefully maybe talk about it after class.
Okay.
If we get disconnected, I can just call you, Ruth, and we can talk over the phone with him there as well. Okay, so here's what this graph looks like. Okay, and they also give us this point. Okay, so just to give you a visual. Okay, so graph F, which we just looked, okay, and the secant lines. Who can tell me the significance of when we know something is a secant line? Here's what I've got. Say this is 4, 2. What's a secant line do in relationship to? It's a line, so I need to draw a line. What will it do in relationship to this? It will intersect it in 2 points. Tangent line 1 point, secant line 2. So this is point 4, 2. So it says in the secant line passing through the point 4, 2, that's this, and Q, so they're going to give us different values of X. Okay? All right, so this is saying that I want to go over 1. Well, I've got to find its output. How do I find that ordered pair? I put it in here, right? If you were to create, here is, let's say 1, 6, 7. So to find its output, we would do the square root of 1, the square root of 6, the square root of 7. So we know that this is 0.11, right? So 1, 1 over 1 up 1. If I connected those, that gives me a secant line. How would I find that slope? Yep. So you're using 4, 2. So we would just do 2 minus 1 over 4 minus 1. So we would get what, 1/3? Do not put 0.33 in as your answer. We're going to be exact. So we're going to do 1/3. Okay. So then of course here you'd still use 4, 2, and then we would use 1, the square root of 6. Nope, sorry, 6, the square root of 6. Okay. What does that look like? I don't know. So what would that be? I would do the square root of 6 minus 2 over 6 minus 4. A toggle. So look, it might say, I don't know what it's going to want as I'd have to see what the answers. Okay, it says 3 decimal. Oh yeah, right there. Thank you. So this one even, this would be 0.333. Oh, it wants 1/3. Yeah, so read your directions. So for this one, it wants 0.333. So for this one, its slope would be 0.225. Okay, and then I'm not going to do the next one. I think you get the idea. Okay, now I don't love, this is asking you to kind of see what is happening as it approaches this. Here would be my tangent. So ultimately, it's kind of wanting to know what that slope is of the tangent line. Let me show you how to find that one. I don't love how they do that, okay? All right, so the tangent line hits the point 4, 2. You agree with me on that? Right? Okay. What we don't have is that second numerical value. So I'm going to plug in the general. What is my x coordinate? Well, that is some x value. What is the output? Well, the output is the square root of x, whatever you would calculate that to be. All right, so here's what I'm going to do. If I wanted to find the slope of this, this is your x1, y1, this is your x2, y2. So my slope would be y2, which is the square root of x, minus y1, which is 2, all over x minus 4. Okay? All right. Now, at this point, what you could do then is do, you could, so we have the 0.42, so you could do the square root of 4 minus 2 over, then we're going to do 2 minus 4, but what's going to happen? We'll get 0 over. That's we know our slope's not 0. Okay, so I can't do that. All right, so this is the part you wouldn't know to do. All right, let me ask you something. If this were x squared minus 4, what would I have in the denominator?
0.
I'd have a difference of 2 squares, right? Okay. I can force this to be a difference of 2 squares. Let me show you how. And this is just algebra manipulation. So let me show you what happens. My numerator is still the square root of x minus 2. We know a difference of 2 squares is always 2 binomials, right? We know a difference of 2 squares. One of them is always plus and one of them is always minus, okay? All right, well, this is the problem, right? Because it's not x squared. This is the problem, so let's go to 4. Well, what times itself is 4? 2. So we know this is 2 and this is 2, right? All right, so what I want to figure out is what times what, that's your first times your first. So what times what, I'll do a dot, would give me x. I need something times itself. I need what's here and here to be exactly the same.
Why?
Well, x times x is x squared.
X times squared times x square root of x.
No, oh no, they can't.
Okay.
No.
You said a word in there that's going to get me where I want to get. So what times what would give me x?
Would it be like the square root of x times x squared?
How about the square root of x times the square root of x?
Um,
Because isn't that the square root of x squared, which is x? Okay, so I'm going to force this to be the square root of x times the square root of x. Okay, now look at what I've got. Do you see something that allows me to do algebraically? What can I do?
Cancel the.
Those are the same. I can cancel them out, right? Okay, so now I'm left with 1 over the square root of x plus 2. Now think in relationship to that 0.42. So now when I plug in 4, will I get 0 in the numerator? I'm going to get 1 over 2 plus 2, which is 1/4, which is 0.25, which is your answer there. Okay. Now, we just worked that together. I don't know if those are going to change or not, but you at least know the process. But students have struggled with that one in the past, which is why I wanted to do that one. Okay. All right. 2.1, done. Do what? Yeah, it's due tomorrow. All right, 2.2 is what we're going to get started on. Okay, the bottom of page 2.1, I introduced this word in relationship to calculus, limits. Okay, and again, what a limit tells us is what it's doing as it approaches. So you're going to see those two words go hand in hand. You're going to hear me verbalize that a lot. So we got to have an understanding of what that represents. Okay. All right, so when we're finding the limit, we have 3 different ways we can do this to find ultimately our final answer. We can do the numerical method, which means we're going to construct a table. Hint, that's why this table is here. Okay. The second way is either to look at a graph, whether that be a given graph, you look at it in Desmos, or you create the graph. That's another way we can ultimately find the limit. And then lastly is the analytical approach, because we're going to have to apply some algebra. Okay. All right. So let's go through this. All right. Let me show you. Typically, you're going to see brackets or parentheses around here. Okay. Let's talk about what this is new terminology and new symbols. This reads the limit as x approaches 2. This means as your x variable approaches 2. So think of a number line, or actually a graph. Here's 0, 1, 2. Here is 2. So what that means is as x approaches 2, it has 2 different ways. It can approach it from the left. So if you'll notice, that's where I get these numbers that are smaller than 2. Notice I started out at 1.75 and I am approaching and getting closer and closer to the value of 2. Because ultimately we're looking as x approaches 2. All right, you can also have x values that approach 2 from the right. Those numbers are going to be slightly larger. So that's why I have 2.1, and then I'm going to get closer to 2, and then even closer to 2. Okay? All right, so this would be, if I were to graph, to look at this as a graph, this is what I would put into Desmos and graph. Now, why does this say x cannot equal 2? What's it? Of the denominator. Yeah, because it would, if I just did direct substitution, I would get 2 minus 2. The denominator would be 0. That's undefined. So that's why we want to look at and say, okay, it's undefined at 0.2 when x is 2. So what's going on as it approaches 2 from both sides? So here's what I want you to do. I want everybody to choose one of these numbers, substitute it in to this equation, and I'm going to ask for that output. So just pick one. And we're going to look at what's happening as we approach from the left and as we approach from the right. So pick one, and then you're going to help me fill in these numbers. And this is step 1. I mean, this is the first approach by constructing a table. So when you get something, so Zoomers, you can unmute and chime in. Okay, which one did you do? This one? What'd you get? Okay. All right. Somebody in Tonkawa. Dylan and Ponca. Give me some numbers. Wait, did we lose Tonkawa?
We're here.
Oh, okay, good. I just couldn't see you.
I have the 2.001. I got 1.001.
I did, 1. I got 0.99.
I'm going to start calling names individually. I've only got Enid people answering. I need somebody else to chime in.
1.75. And I got 0.0.
Okay, that's what I got too.
Ruth, you got somebody that's got one for me?
It would be the same answer on 1.75.
Okay. Somebody else in Tonkawa do a different number that's not been used?
On which one?
I did 1.75.
That one I
I
got.
got 0.748.
Okay, and we're gonna 0.75. We're gonna go with that. But thank you.
Okay, A 1, we got,
No, 2.1. Just the 2.1. I got 1.1.
Thank you.
sorry,
Do I have anybody that has 2.01 or 1.99?
I have 2.1, 1.1. Oh, already.
Yeah, that one I got. All right, I'm going to give them to you, but this is something that you'll have to do on a quiz or a test possibly. 1.99 is 0.99. 2.01 is 1.01. Okay, so again, at 2, it is undefined because it is the denominator of 0. But as we approach from the left, what does it appear? What numerical value would you guess it is approaching? 1.
1.
So it's approaching 1. What about from the right?
1.00.
And then if we did 0.001, we'd more than likely get 1.0001. And then 1.0. So what is it approaching ultimately? 1. So this also approaches 1. So what that tells me is if I had this graphed at point 2, there's nothing there because it would be undefined, but the graph is approaching the same output of 1. So that's the ordered pair 2, 1. All right. So I'm going to look at this as a graph. So that would be if you went to Desmos, okay? So notice we have the 0.21. So I'm going to go over 2 and up 1. Now I am going to do an open circle because why? Because it's undefined at that point. But, sorry, I just want to get a good indication. Oh, my land, I cannot. Hang on, I'm doing something in my head and I'm not doing it well. Okay, so what we've got is, if I were to sketch this, it would look something like this here. This is what it would look like if you were to graph it. Okay, so let's talk about at this point, like I said, this is your ordered pair over 2 up 1 because it goes over 2 and then your output is 1, right? Okay, so what this looks like in a graph and what we would ask ourselves is, as I approach on the graph from the left and as I approach on the graph from the right, what is it approaching? Okay, so here's some symbol and mathematical writing of this. F at 2 does not exist. Why? Because that would make this undefined. Okay, now that's different than the question of the limit as x approaches 2 for that function. What is its limit? Both of them are approaching the exact same output as 1. So it's the same graph, but 2 completely different questions. And students have a problem with getting those kind of switched up. Okay, lastly is to approach it analytically. Okay, so I'm going to write the limit as x approaches 2. Now I want you to look at that numerator. It's a trinomial. What might we be able to do with that trinomial? Factor it, right? So what I'm going to do is I am going to factor that numerator. This is where my expectations are, is that you can factor that fairly quickly. To trinomial, we have the leading coefficient of 1. So we ask ourselves, what two numbers multiply together to give you +2, add together to give you -3? That would be -2, x minus 1. That denominator is x minus 2. Now, why is that helpful? Because that will cancel that denominator. So now we have the limit as x approaches 2 for just x minus 1. So what we've done is we've removed that whole. We've removed that whole. So now what I can do is just plug in that value. So when I plug it in, I drop the limit notation and I would just say 2 minus 1 is 1. So the limit is 1 from a table. The limit is 1 from my graph. The limit is 1 when we do it algebraically. Okay. All right. So now we're going to do this equation. This one's a bit more involved. All right, be sure that when you plug in correctly, okay? Time-wise, because we're a little behind where I would like to be, I'm going to give you the outputs that are going to occur, okay? All right, so when you plug in -0.01, this is going to be 1.995. So I would highly recommend that at some point you plug it in. You don't have to do all of them, but just to make sure you're getting the same output. If you're not, then you're doing something incorrectly in your calculator. Let's get that fixed now. Okay. All right. -0.001 is 1.9995. And notice here we're approaching 0. So this is what we're approaching. We're approaching the x value of 0. All right, and then for this value, so it's the same number, but you're going to have 4 nines. 1.99995. Okay, so if you start seeing that pattern, what would you say it's approaching? 2. All right. So we have determined that as we approach from the left, it's approaching 2. Okay. If I go to the 0.01, that is 2.005. 0.001, guess what? You're just going to add another 0. 2.0005, guess what? You're just going to add another 0. 2.1234 zeros and a 5. So it appears as we approach from the right, it is also approaching 2. So since they are approaching the same value, I can say that graph is approaching 2. Now, what would have happened if we would have put 0 in for here? We would have gotten 0 plus 1. The square root of 1 is 1, and 1 minus 1 is 0. So in this case, we know x cannot equal 0 because that would make the denominator 0, and that does not, that's undefined. Okay? All right, so that's what it looks like as using the table. So now we're going to do what it would look like as a graph. I'm going to try to get that correctly put into my calculator, or my phone in this case, but Desmos. Whoops. Okay, and we just at 0, 2. Okay, so this is what that graph looks like, okay? So at 0, 2, it's an open circle because that is undefined, okay?
Do approach 4, approach 2 or Do you have to do the numerical approach to be able to do the graph?
No, you can go straight to the graph. Yeah, you can do each of these independently of the others. I'm just showing you all three. Okay, I'm going to best sketch this as I can. So it looks something like that. Okay, it's not great because those don't look like they. So sorry about that. Okay, now if I ask you what's going on at f at 0, so that would mean you would plug in 0 here. What would you tell me? What happens if I directly plug in 0? We just calculated it. It does not exist, right? Because we got the denominator of 0. We talked about how x cannot equal 0. So this does not exist at that point. When you see the limit as x approaches 0 for that function, we're not wanting to know what's going on at that point. We already know it's undefined. We want to know, are they approaching the same output? Well, what ordered pair is that? 0, 2? Aren't they both approaching the output of 2? Which is what they were both approaching. Okay. Now, the algebraic approach is a little bit more of a booger on this one because look, we have that square root in the denominator. All right, so this is going to require a little bit more work. All right, we have the limit as x approaches 0, and we've got x over the square root of x plus 1 minus 1. We don't want that radical in the denominator. We need to rationalize it, but it's also part of a kind of a binomial with this minus 1. Does anybody remember how we rationalize that? Conjugate. Perfect. Okay, so let's talk about what is the conjugate of this. It is the square root of x plus 1 plus 1. So these two terms are the same. The only thing that changes is your sign. Had this been plus 1 here, then I would have put minus 1 here. Now, we're doing something algebraically that is not changing its value, which means the only thing I can do is multiply times 1, right? So that means this has to be the square root of x plus 1 as well, because technically this is multiplying times 1. All right, so now if you'll look in the numerator, we have x times the square root of x plus 1 plus 1. You could have gone ahead and distributed. That's fine. Okay, the denominator is a bit of a booger, so think FOIL. So first times first. Any time you multiply something under a radical times itself, it just eliminates that radical. So we are left with x plus 1. Now, the reason we multiply times a conjugate is so our O and our I will be opposites and they subtract out. So if we did outside, we get positive the square root of x plus 1. Inside, minus the square root of x plus 1. Those subtract out. It's gone. And then last times last, -1 times +1 is -1. So when I simplify this algebraically, then we are left with, now I'm going to distribute this, x times the square root of x plus 1 plus x times 1 is x. And in the denominator, 1 minus 1 is 0, so I'm left with just x. Now, if we do direct substitution by substituting that 0 in for an x, it still gives that to me, right? Okay, what do you notice about the numerator? I can. I'm going to do one more step. I'm going to factor out, see how this has an X and this has an X. So I'm going to factor that out, which we just had it there. I should have just left it. Sorry. I shouldn't have distributed. I wasn't paying attention. Sorry about that. We're just going back to where we were. Why? Because that allows me to cancel this with this. So now I can direct substitute. So I'm going to put that 0 in place here. 0 plus 1 plus 1. That's the square root of 1 plus 1, which is 1 plus 1, which is 2. All of that work to get to the 2 that we already knew was the answer. Right? Okay, that's where we're going to stop, and that's why I'm concerned. I'm like 2 pages behind where I was last spring. So we're going to have to try to get kind of caught back up. So you have 2.1 is due. So you have something due tonight, right? 1 point something? Is anything? No. Yeah, that review day 2. Review day 2 is due tonight. 2.1 due tomorrow, and then I have not set another due date yet. Okay. Miss Ruth, yes, I should be able to get that done before 5.
Thank you.
I'll make myself a note to do it first thing when I get back to my office.
Sounds good.
Yeah, so Xander, be watching for that. Actually, I could have gone a little bit further. I was thinking class ended at 11:15, Fuddruckers. Since I already let you go, I'm going to let you go. I should have gone on to the next one, but we'll start there tomorrow. Ruth, when did I tell you that that quiz might be?
Susie, the first, is that?
Okay, first quiz will more than likely be next week. I'll look at this better and let you know tomorrow. Okay? All right, let me know if you have any questions. Otherwise, you can leave or disconnect.
And Brandon was a no-show.
Okay, thanks for the reminder. Yeah, you guys are good. Jacob, are you needing me or you just haven't
I was just-
disconnected?
I was just going to let you know, currently I'm in between housing and my internet connection is not 100%. I dropped out in the middle today. But I got back on. I just letting you know if I drop out, it's something on my end, at
Okay.
least until I can get internet
Okay,
sorted out
well,
here.
hopefully that can get fixed pretty quick. So, all
Thank
right,
you.
thanks for letting me know.
You have a good day.
You as well.